delay, let us start the first session. And so the first speaker is Rafael Porto, who is lead scientist in the DESY Institute in Germany, and he will be.
Did she freeze or?
Yeah, it looks like she froze. So
Okay.
we're not wasting time. She already mentioned your name and your affiliation. And let me just read the title, Bootstrapping the Two-Body Problem. I'm sure we'll get back to the speaker. If not, one of us will do it. So sorry about those technical glitches. I'm sure.
No, don't worry,
So,
please.
Rafael, welcome. And the floor is yours, please.
Thank you very much, guys. So I'm going to tell you a little bit about some recent developments on using quantum field theory and amplitude techniques to study the two-body problem in general relativity. And I'm sure we're going to hear more throughout this workshop about various different approaches. And I should say, Cheng-Wen Liu will also talk about similar ideas that we'll probably not cover in detail in this talk. So, okay, why is the okay? So by now, I don't have to introduce gravitational wave science. You all guys know that we open a new window into the universe, but I think it's important to emphasize that LIGO, Virgo, Kagra are, at the moment, discovery machines. We found these supermassive, well, these compact objects in the skies that are producing gravitational waves, but the future with the Einstein telescope and LISA will be high precision machines that will tell us whether ultimately those we think are black holes of general relativity, but those massive compact objects that are producing gravitational waves are indeed the ones predicted by Einstein's theory. And I make this point almost every time I give this talk, because if you think about this is the era of astrophysics, the 2020 Nobel Prize that was given for the discovery that is a supermassive compact object at the center of our galaxy, they didn't say a supermassive black hole, they said a supermassive compact object because we really don't know what is sitting in there. It could be the Einstein's theory of gravity described this object, but it could be something else. It could be modified gravity. It could be another object, another supermassive compact object that has nothing to do necessarily with the solutions of Einstein's equations, even though Roger Penrose got the Nobel Prize for proving that you almost always form a black hole. The jury is out there to know what is it that these objects are. Fortunately for us, nature is very kind to collide these objects in the sky. We measure the product in the form of gravitational waves and to high precision measurements, so trying to extract the waveforms and seeing the contracts in this prediction with Einstein's theory, we can ultimately tell whether these are indeed the objects that we expect, or perhaps there are new surprises out there for us to discover. So that's the main goal for us. It's really going into the discovery potential of gravitational wave science that relies on us to be able to make precise theoretical predictions. The same way, by the way, that we do in colliders and detect the Higgs over the background, we need to understand those backgrounds very well. So what is for us our standard model? So what is the challenge for us? So we do have a standard model. The standard model is a classical theory, of course, even though we're going to use quantum field theory methods. But our standard model is Einstein's theory of gravity, plus whatever matter we think we understand that forms the compact objects out there, for example, neutron stars. So for the most part, we have like the Lagrangian of QCD, if you want, or neutrons and protons that form the neutron star. And on the left-hand side, we have Einstein's theory of gravity. So what is the name of the game? The name of the game is to have those two objects, those two compact objects, go about for, in principle, go about for millions of years, but we don't get to see much of that because the gravitational waves are very weak, they're very far apart, they get very close, and in fact, we only see the last few minutes of this dance, and then they spiral, they collide, they merge, they form a black hole that rings and produces gravitational waves, and then whoop, it settles, it's done. There are no more signatures of gravitational waves because we form this final, we think, black hole. So there's these three regimes in the dynamics. There is the initial regime of the spiral, in which we can use perturbation theory, analytic tools. This is very fast because we can produce waveforms just by doing analytic calculations. Then comes the merger part, which is the harder, fully non-perturbative part of Einstein's theory of gravity, which right now we don't have analytic tools. We have some approximate tools that we can use, and I'll maybe say something about that. It's exact, but it's very slow. Running one simulation could take months. So we don't want to waste. In fact, they cannot possibly cover the 10 to the 5 cycles that we might be able to see with future detectors. So you cannot run simulations for the entirety of the waveforms. So we use the merger phase to match into the spiral and construct a waveform that then has the ring down and produces the template bands that we use to search in the data. In this talk, I'm not going to cover numerical or the ring down analytic tools for the ring down phase. I'm going to concentrate on the inspiral part. And here's where most of the waveforms appear and occur. This is the part in which perturbation theory, or the so-called post-Newtonian expansion, has been very popular to produce the waveform models. And this is a part in which we can, even though it's approximate, even though it's difficult to find exact solutions in a theory like Einstein gravity. If you there's a beautiful talk by Ed Witten online that you can hear him discussing about it's not worthwhile solving exactly the systems that you can solve. So the hard problems are hard because we cannot produce exact solutions. And that's what we're going to do here. It's a very hard problem, but a lot of tools have been developed recently in the past and very recently with ideas also in scattering amplitudes to tackle these problems precisely in this inspiral phase in which we can approach with analytic tools. So that would be the name of the game for us. We have a lot of cycles in band at design sensitivity, lots of events. We need to produce high accuracy waveforms, and this is what we want to produce as what I like to call gravitational wave precision data. This is producing the backgrounds that we do also for the Large Hadron Collider. The same thing we're going to do with thousands and hundreds of thousands of templates to search in the data for the black holes of GR or anything else that is out there in nature. So very good. So through a concerted of, so this has a long history, and I cover a little bit in a second, of since GR was developed like 1915, then even Einstein himself started studying perturbative regime, producing the gravitational waves, the first post-Newtonian expansion, and so on. So it has been a long journey for many of us in producing high-precision waveforms. So where are we right now? Where is the state of the art? So this is a concerted effort. There's a lot of tools that I'm sure also Laura will mention and talk about. And the one I'm going to concentrate on is these ideas of using this wall line or effective field theory methods to the two-body problems that you'll see maps the two-body problem in gravity to similar ideas of people studying QCD, like bound states of QCD, heavy quarks, and so on. Right now, we are at the fourth order on post-Newtonian accuracy. What does that mean? That means that if you start with Newton and 1/r, we go to next to next to next to next to leading order, and even the gravitational wave phase evolution have been computed to this order. There are partial results that are also known at fifth post-Newtonian order in, for example, the binding energies, but the fluxes has not been computed yet. This quantity here is the change in the orbital in the orbital frequency in time, and that's orbital frequency is what we will observe as we the detectors, interferometers measure how the wave stretches and shortens the path of the light. And that's exactly how it's correlated directly, this phase evolution, with the orbital motion. For example, a leading quadrupolar, in a leading order quadrupolar order, we know that the orbital frequency and the frequency of the gravitational waves are related just by a factor of 2. And therefore, this is, for example, the celebrated quadrupole formula. And this is the quadrupole moment that tells us how the gravitational waves are emitting, for example, in linearized gravity. But then you keep adding higher and higher order corrections. And right now we are entering this fourth order, which really is like a for-loop calculation. And then if you ask yourself, holy cow, we are at the fourth order in the perturbative expansion. Are we done? Is this already enough? Are we ready for the future of gravitational wave science with such high precision? And the answer is no, and not even no, it's not even close. If you think about what observatories like the Cosmic Explorer of Einstein telescope are going to see by the age maybe of between 2030 and 2040, we don't know exactly how this is going to go, but LISA will also be in the sky probably sometime before. There'll be so many detections, so many events, and the detectors are so good. If you compare, for example, what in cosmology, what happened to like the measurement of the anisotropies in the CMB. At the very beginning, we had COBE. There was again, as a discovery machine, they detected the anisotropies, so they couldn't say much. And then 20 years later came Planck, and we could see a lot of details in the anisotropy. We learned a lot about the early phases of the evolution of the universe. Well, the same is going to happen to gravitational wave science. LIGO and Virgo is like our COBE, our discovery of gravitational waves. And then LISA, ET, Cosmic Explorer will come, and that will become our Planck. That will become the high precision that can really rule in or rule out a lot of the physics of gravitational wave interactions and compact objects. So not even close. We are not even reaching the level of precision that is expected, the empirical reach of these detectors, because the waveforms are going to be very complicated. It's a lot of structure in these waveforms, different mass. So this is the vanilla one of circular aligned spins or even no spins. If you have a mass ratio which is not 1, then the waveforms are different. Non-circular orbits, you have eccentricity, you have different modes. Then you have aligned spins, then you have misaligned spins. The orbit is not planar anymore. So all these details we want to be able to extract from the waveforms, this is not good enough. We will need higher order waveforms, better templates. Even if you don't believe in anything exotic at all, we still need to go deeper in the analytic understanding and overall the construction of waveform models. And this, of course, brings the challenges and opportunities of gravitational wave astronomy. Another thing which is very clear is that gravity is very special. You know, you free fall, you don't feel anything. What does that mean? That means that you're only sensitive to curvature. Curvature means that derivatives of space-time. If you're in a point, you don't feel anything, you move a little bit, and then you see the curvature of space-time, and that costs you 2 derivatives. Each derivative of a potential, say, potential 1/r interaction, will cost you, because each 1/r scales like v squared, like the virial theorem, and therefore many derivatives cost you a lot of velocities, higher post-Newtonian orders. And it so happens that the first effect in which you can see a tidal deformation of the object starts a 5th post-Newtonian order. That's a phi loop effect. So the first time you can see tidal deformability of a neutron star, say, is a very high post-Newtonian order. It's a very small effect that appears very late in the spiral, and for the most part, initial LIGO, advanced LIGO now sees a little bit of those effects. Certainly, the Einstein telescope will be sensitive to those effects. So to really distinguish the objects, say you don't have a counterpart, you don't know that there was a neutron star because there is no light, and you want to know whether that object was a black hole or something else, you have to see the level of precision that is accurate up to these tidal effects of the 5th post-Newtonian order. Of course, there is also the spin, and you can say the quadrupole moment of a rotating black hole is different than the quadrupole moment of a neutron star or any other boson star or any other object. Of course, the spin will also tell, but the spin has a lot of degeneracies as well. It becomes a much more complicated observable. And therefore, it's much cleaner if you have something that has no spin and you measure this effect and it's not 0, and then you see something which is not a black hole. And why do I mean by that? Because black hole has 0 love number. And this is something that has puzzled relativists for a long time. Now we start seeing a little bit more of what this means instead of properties of the solutions of Einstein gravity in 4 dimensions. But from the point of view of the long-distance physics, this looks like a fine-tuning. Why wouldn't the black hole generate some quadrupole if I put it in an external gravitational field? It turns out that it doesn't, and that means that if you see something in the data that is heavier than a neutron star, say 10 solar masses, 20 solar masses, it has a non-zero tidal deformability, then it's front page of the New York Times. That's a new object in nature that we have never seen before. And therefore, this is a beautiful handle into new physics. But to get there, once again, we need high precision waveforms, and that's exactly what this motivation is about. Why did I basically introduce all of this? Just to tell you that there is a lot of discovery potential. A, because the machines are going to be great and our waveforms are not good enough. B, because if we want to distinguish what those guys are, we need to measure these tidal effects. We want to see effects which have to do with the size. And if you think about what quantum field theories and high energy physics do, you want to see the UV physics on the IR dynamics. That is often what we do in terms of these high dimensional operators and so on. So these tidal effects, they serve as a high dimensional operator of new physics in the gravitational waveforms that happen to scale with a very high power of the expansion parameter. Therefore, to see it, you need to have your background up to that order. And that's essentially what we want to do. And this is what I'm going to tell you about how we construct those waveforms with these ideas, this framework of this effective field theory approach, both in the very traditional post-Newtonian expansion that people are very familiar with, but more recently with the study of scattering or post-Minkowskian expansion, which has resurfaced now with some ideas from scattering amplitude to produce also waveforms for scattering, which could also be seen by future detectors. We can get bursts. Also, if you have highly elliptic orbits, they might look like, as you get close, that little turn is like a scattering process, and you might model the waveform just by a bunch of bursts. And that could also be done in the post-Minkowskian approximation. But more importantly, and this is the most exciting part, is that maybe, and that would be the second part of my talk, maybe I can take the ideas from this scattering and map to the bound case, what we like to call the boundary to bound dictionary, which says, okay, you have an observable for the scattering. I can construct from there an observable for the bound case. And that's beautiful because then you get for free a lot of these resumations of the velocities that the post-Minkowskian expansion brings to the table. And that's going to be the name of the game. So very good. So how does this work? So how is this effective field theory approach? So very schematically, even though I'll try to answer questions if you guys have any, the idea is that there are very clear separation of the scales in the problem. You have the size of the object, which is my UV physics. Then I put those two guys with different UV physics. This could be a neutron star and a black hole or something else entirely. We don't know. There are different scales here that matter on the scale of the size of the objects. Then there is the binding forces, this one over our potentials. And then these guys move slowly, in principle, slowly, small velocities, and they're producing the waveforms, which are down by a factor of V because the typical wavelength of the radiation is R over V, and V is less than 1, and therefore that's another separation of scale. So there's a very beautiful separation of scale, size, binding, radiation. And therefore, we can implement this idea of the effective field theory approach or framework, if you want, which is we can disentangle one scale at a time. First of all, we're going to treat this completely classical. So we don't want to get lost into all these quantum technologies of loops. However, there will be loop-like calculations because we're going to iterate Green's functions of a nonlinear theory. And this is going to resemble exactly what we do in loop calculations. There will be no internal gravitational loops, but when we iterate the Green's function, and as we're going to see, we treat the bodies as pawn-like objects, the typical momentum of that Green function could go all the way to infinity because you can go all the way to 0 in position space. And that will resemble a loop integral in quantum field theory. And that's, as we will see, will be very resembling of what we do in collider physics, and that's why these tools are going to pop up. But always we're going to be in the classical regime. We will always be on classical Einstein's theory of gravity, but we can treat it as a quantum theory by saying, okay, there is some partition function, there is some effective action of the theory, there are different scales. In short distance, there is the full inner structure of the body, there's the 1 over r potential binding energies of gravity, and there is the wavelength of radiation. So if I integrate out, if I solve for all those modes of the gravitational field, plus whatever is inside the body, like the neutron stars say, then I solve the theory. The theory is done. The same way that the QCD, lattice QCD people compute these Wilson loops and they get everything, we can do exactly the same. Now, this will give us all the information that we need. What is the information that we need? Well, we need to know the waveform. We need to know like the binding energy, the equations of motion, and so on. Everything will be encoded in this function. And that's going to be the name of the game. So the first scales that we need to treat is the size of the objects. And then we integrate out from the point of view of the other guy, the companion, the object looks like a point. So we're going to integrate out this part of the action, which is the 1 over RS scale, the very high UV modes of the theory. We're going to match into a point-like object. And here's where these tidal effects are going to appear. We're going to treat now this as a word line. That's going to have an MD tau. So all the inner structure is going to go inside the mass, which, by the way, I don't know how many undergraduates are here, but when you write MD tau in relativistic dynamics, just classical relativistic dynamics, that M is not the sum of the masses. Otherwise, the masses would just fly around, fly away. They're bound. The bound means that the M of the neutron star is not the sum of all the neutrons and protons. So there's binding energy there. But that's a matching coefficient. I don't know. If I tell you what the neutron star is, what is the mass? We don't really know. That's an observable. So that's a matching coefficient. The same we're going to do with the tidal deformability. There will be some quadrupole deformation. And it's going to couple the same way that the dipole deformation of a charged sphere will couple to the electric field. This guy will couple to the electric component of the Weyl tensors, two derivatives of curvature. And it's the Weyl tensor because traces are going to vanish. These things are symmetric trace-free because on shell, on solutions of Einstein's equations, the R mu nu of the theory away from the point is always 0. And you can always remove it. And therefore, you have a beautiful wall line theory now that describes neutron stars, black hole, or whatever is out there that's going to have some tidal deformation that's going to then land on the waveforms. After we integrate out this scale, which we don't know about the UV, it could be any new physics in there, the rest is completely known. This is now Einstein gravity. This is literally solving Einstein equations with point-like sources. And this partition function has two components. It has a real part and an imaginary part. Now, the real part is the binding. It's going to give us the binding energy, the equations of motion of the system. And the imaginary part is going to give us the fluxes, the width of the state, my value for. And this basically is just do the calculation of the partition function. You get real and imaginary part. The real part gives you the binding energies. The imaginary part gives you the fluxes. With that, you can already construct waveforms. And this we do the same way that we do in quantum field theory, except that you don't have closed loops. However, because we are now treating this guy as a point particle action, remember, it's the point particle action of a localized source, the type of diagrams that we get, this is completely tree-level, but these J's are localized sources, are point-like objects. So this iterated green function will look like a loop, but it will be a classical loop in which an iterated green function with a point-like source will look like a loop on quantum field theory. But we are not doing anything fancy. We're just literally solving the field produced by the sources and plugging it back on the source. And this is what people did many, many years ago. In fact, it was originally the ideas of Wheeler and Feynman in computing precisely with the Feynman propagator that also gives you the optical theorem and the width. I'll tell a little bit more in a minute why we're using these boundary conditions for the field. But in the region in which we care about binding, for the most part, these are the so-called potential modes in which the green functions are quasi-stationary. There's a 1/r potential and you moved a little bit, so you do have a retardation, but you expand that in powers of V/C, and then that gives you corrections of the propagator, this P0 square over P square, and you can do that systematically to all orders. This has been done. This is like, since Feynman, it was done by Duff to recover, for example, the Schwarzschild solution, and it was done by Thibault and company to compute potentials. It's very similar. This is not the way that the effective zero approach introduces a new look into the problem. This is more or less standard. What is the new look? The new look is that there are two scales here, potentials and radiations, and I want to go now into the radiation scale. What do? Here comes the fun. I can disentangle completely those two scales in the post-Newtonian regime by integrating now first the potentials, matching to a theory in which the whole binary now is a point with some multiple moments, and in that theory compute the radiation loops, the radiation integral. So after I do that matching, I make a very complicated integral that in principle has many regions and very high order in the loop expansion. Say a 4-loop expansion calculation, I can make it a 2-loop potential matching and a 2-loop radiation integral. And that makes your life significantly easier. And that's why these tools are very powerful to compute higher post-Newtonian order. As we will see, the post-Minkowskian approximation will try to bypass this, and it will give us a resum version of this multiple expansion. The trade-off will be much more complicated integrals, but the ideas are very similar. So it's really decoupling the different regimes, the different regions of integration. This is also called sometimes the method of regions, and this is one of the key ideas of how these post-Minkowskian and post-Newtonian approaches are going to work out. So that was the light introduction of what we do, and I'll be happy to answer questions later. So where are we right now? For post-Newtonian order, as I mentioned, we haven't yet finished this 5th post-Newtonian order where the new threshold physics will start. And I'll tell you why we have a little bit of trouble with that. But we do understand very well up to 4 loops of these iterations. And again, we want to get here because of this threshold, because of the detectors being so good, and because of the threshold of detection of tidal effects that starts at 5 p.m. And that's why we want to get to high order. I mean, it's not just because we can do it, but because we can do it. I mean, you can always create these new tools and ideas and open new ways to think about the problem. So conceptually, it's interesting. But practically, we need better waveforms, period, just to learn what's out there, even population studies. So a measure spin of the black holes is already a difficult task. So this is why we justify doing what we're doing. That's what I still tell myself. This is not just fun, it's useful. So first post-Newtonian order, and I see I talk a lot and I don't move fast. So I'm going to start picking up pace. Just to tell you how this was done, right? If you go back and look at the 1 p.m. calculation of Einstein-Hoffmann, which, by the way, was first done by this guy Drosten many years before the paper of Einstein-Hoffmann. This guy produced this solution in 1916, and it was communicated by D. Lawrence. And this paper is from 1935, right? So 20 years later, it was rediscovered, as it happens always. And it's a very complicated calculation by Einstein and Verhoeven. Some surface integrals of some conservation of T mu, very complicated. How is this done in our theory? Well, it's trivial. You have a one graviton exchange, you expand the Green function, and then you get a v-squared correction there, this v-squared correction, and then there's some nonlinear cubic coupling, and then you get the first g-squared correction. Semi-trivial. So nice that I put spin on this for my thesis, and we got a completely new result. Already at 3 p.m., because the spin adds p.m. Counting, we were able to compute the nonlinear spin interactions of black holes by using precisely this framework, and people could not do this before because of this idea of disentangle the divergence sum, the short scales, the different modes, and so on was very complicated. This tool was very clean, very simple, and we were able very quickly to produce a new result. So where are we right now? So you start iterating this Green function, they look like loops, and that's what I mean by this type of integrals. Now in post-Newtonian, this type of integrals are three-dimensional integrals. We expanded the Green function in retardation, which means we get static integrals. And that's why we can do now 5 loops static integrals, because they are much easier than 5 loops relativistic integrals. And therefore, these master integrals are known up to 4 and 5 loops. In fact, the master integrals of the even loop order already fix the odd loop order. That's also very nice. All the master integrals are 4 loops, which were very hard to compute. They give us the 5 loops for free. It's just the way that the power counting works in post-Newtonian. That's not true in PM. But then here we start getting the fun. We start getting the new physics that is not there in traditional theories like electromagnetism. It is kind of there in quantum mechanics or in QCD, in quantum effects, but not there classically. What is it? Well, there is an effect that dresses the binding energy of the system at 4 post-Newtonian order that happens to do with the radiation being scattered off the geometry and coming back, like radiation reaction effect. That's called tail effect. And this tail effect was already entering the classical binding energy at 4 post-Newtonian order with a logarithm of the velocity. So the post-Newtonian expansion is usually g, v squared, v4, v6, v8, g squared, v blah, blah, blah. Now we get a log of v. And this log of v resembles exactly the same that happens in the lamp shape. The beta log is literally the same that is happening here. It's so much that I wrote a whole paper showing how this is the same. But this creates a lot of trouble because this is due to infrared divergences now that appear in the theory. And then you start seeing how this becomes very subtle. Long distance effect coupled to short distance effects, IR effect, local UV effects. How do you treat all of this? And it so happened that in the standard approach, people started running into all kinds of ambiguity parameters, infrared divergence that they didn't know how to regularize. The way this happened is simple now in the effective field theory approach because this is done for us automatically. In fact, for the lamp shift, even Feynman got confused. Feynman did this calculation for the lamp shift. I don't have time to explain this. He got it completely wrong because he was also confused about this infrared divergence. And in fact, the first ones to do it correctly were French and Weisskopf. And then Vita obviously did these calculations too. Dyson and other people, and Lamb. Lamb was an experimentalist, but also wrote papers in theory. I mean, you see what these people in the 50s, what they were able to do. But even Feynman got it completely wrong. And then he wrote a very famous footnote in which he apologized, footnote 13, to these guys for actually not understanding what was going on. So this is very subtle. But the effective visual approach naturally separates the scale. So this allows us to understand precisely how those long distance effects are entering the short distance effect. And now we enter in the regime in which it's becoming even more subtle. Why? Because not only we get these tail effects, which are very subtle and logarithmic divergence, blah, 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 we get a memory effect, non-linear memory effect. Not only the radiation can scatter off the 1/r force of the binary on the radiation, it can also scatter off the earlier radiation, which is called sometimes the nonlinear memory. The radiation scatters off the radiation, and that comes back. And that can also redress your binding energy. And so happened that right now, we have a discrepancy on what those effects should be. So it's becoming very subtle to the point that we don't have a complete answer yet because of the way these effects enter. And this will be related also to understanding the scattering, because it so happened that the way these effects enter in the bound case or in the unbound case is different. These tail effects become no local in time, and this is also creating a little bit of trouble in mapping one into the other. As you see, it's not as straightforward just doing the integral. there's a lot of conceptual issues that we need to solve. So very good. That was the live review of the post-Newtonian expansion. Now I'll tell you a little bit about the post-Minkowskian approximation, because this is basically what we're doing right now, where the new results have been entering and how we're trying to map this information from unbound to bound. But I wanted to give you a live review of the post-Newtonian expansion because that's where our life started. That's 100 years of history, and that's yet what the most accurate waveforms are. The PM hasn't yet gotten to the same level. We might get there, and we are walking towards that, but we are not there yet. And there's also issues about mapping one into the other. So there's a lot of subtleties involved. There's a lot of work to be done here. It's not as simple as it sounds. So what is the post-Minkowskian expansion? Well, now we kind of switch to another problem. We were talking about bound states, separation of scales. Now we do scattering. What does that mean? Well, now we prepare the states at infinity. So we have well-defined relativistic initial states, special relativistic initial states. So we send this guy with some initial momentum at some impact parameter V, and we just let them scatter, and we collect them at infinity. Why is that nice? It's nice because you never have to see any GR effects. You send something in special relativity, and you get something out in special relativity. You solve the field in the middle by integrating out now the entire self-region, the entire potentials and radiation modes, because now it's a full propagator, it's a full p-square. We don't disentangle these guys anymore. We just do the full integral, but we now collect an observable, which is, say, the scattering angle. So we compute an impulse from the effective theory that the partition function will give me a equation of motion. The equation of motion will give me an impulse. From that impulse, I get an observable. I get an angle. And this is very clean. In GR, we always say, oh, I computed a potential. Which gauge? Which coordinates? And then you run into different coordinates, divergences, because you chose the wrong coordinates. All of that is gone if I compute an observable. And now we're going straight to the observable. The catch in this calculation, why is it not that we do this from the beginning? The interests are very hard. We get the full quadratic propagators, but also the wall lines, the deflections, we treat them perturbatively. What does that mean? That means that when we solve the previous order and we solve for the deflection and then we plug it back into the action, we have to solve for that deflection perturbatively. And the equation of motion is like acceleration, x double dot equal force. Those double dots, they become linear propagators because the double dots become like 1 over omega, and 1 omega to some power. And those are like the omega, you can think about p dot n or p dot u, the velocity, and those are literally these linear propagators. There is no mystery. What happens is just perturbably solving the equation of motion, you get x double dot in Green's functions, inverse Green's functions. Those are the linear guys, and the typical p-squares of gravity are these guys. So the name of the game now is like solve this integral in the entire region. Of course, this guy has quasi-static interactions, but also radiation reaction effects. You want to include all of that at once, and now try to disentangle later with the physics, but the integrals know about everything. So we turn. We were looking at these things this way at every PN order. Now we're looking at these things this way at every PM order. G, G squared, G cubed, G4, but all orders in velocity. We are resumming the whole Green function. Am I doing with that? Okay. So history here is a little bit shorter. Not that much has been done here. Why? Well, A, because it was scattering. People did not think about connecting this with bound states until much later. And then, of course, we didn't have gravitational wave detection, and scattering per se, classical gravitational scattering wasn't that interesting, I guess. So the first calculation of the first post-Minkowskian and second post-Minkowskian, both were done by Westphal in the 80s. This was reproduced using the scattering tools by Cliff Chern, Michael Solon, and Ira Rothstein, which I'm not sure if somebody's going to cover this. Maybe Emil will talk a little bit about this. And then ourselves with this effective theory approach around like 4 or 5 years ago. So you see, we started 5 years ago doing this, and we were matching something that had been computed in the 80s versus the PM that started in the 20s, right? There's a lot of catch up to do. But we are moving really quickly. There was a breakthrough with the 3 PM calculation of Svi, Bern, and collaborators. There is a very complicated calculation the first time they did it. As always, you do a first-time calculation, it's very complicated, the same way that the 4 PM calculation was done by Thibault Damour, Gerhard Schaefer, and Peter Jaranovsky in a super complicated way. And the way we reproduce it and we got the right result without ambiguities or anything was much simpler. But the second time, you always learn something. And it so happened that this calculation is semi-trivial. Right now, an undergraduate can do this calculation that is 100 pages paper of Bernard. And it's just these diagrams, right? It's just computing the two-loop full relativistic integration, but so happened that at this order, it's all dominated by the potential modes. So it's really just doing the resummation of the potentials. And as Chen-Wen is going to explain, this can be done very simply through the tool of differential equations. Why can be done very simply with differential equations? Because there's only one scale in the problem. When you compute, for example, the first correction, this gamma is really the boost factor. What is it that the solution can depend on? The relative energy. And that's literally this boost factor, which is the product of the incoming velocities. This is what this guy Vespal got. This is what we reproduce. It's very simple. It's just a one-loop integral. The two-loop integrals are slightly more complicated. But what people have been realizing, and we started using now for the two-body problem for the first time after some first attempt by Julio Barra Martinez, Mao Zeng, and Enrico Herman, and I might be missing someone, in which they started applying this also for, they were doing the supersymmetric case, and about the same time we were thinking about doing precisely this calculation in pure GR without having to do the very complicated integrals that Svi and company were doing, by just mapping this into solving these differential equations. And if you map into this variable x, which is just how to rationalize the square roots, and Chen-Wen might talk a little bit about this, the answer is just a log. In this variable, which is how gamma maps into x, the full 3 p.m. angle that had this funny arc sinh is just a log of x. It's just an RG flow of the two-body problem. It just tells you that the full PM answer, you compute a boundary condition of this differential equation in post-Newtonian, and then you run in x, and you get the full velocity dependent. In this case, this RG flow was trivial. It was just log of x. Why? Because it was canonical. It just had polylogarithms, and at 3 p.m., at 2-loop, it was just a log. You kept going, and then it became the 3-loop, the 4 p.m., and this was also done, and this was done concurrently. We, the group of B and company and ourselves, we finished this calculation literally at the same time. And how did we do this? Well, they again tried to resum the calculation of the integrals by mapping into a solution that they know. Because what happened here is that you could not solve the differential equation with these canonical forms. It was not just polylogarithms. So it became tricky. And the trickiness came because the elliptic integrals that now appear in the solution that do not allow you to write the differential equations in the so-called canonical form of polylogarithms. But the way we solve them is like you can use the same tools of differential equations. You have to be a little bit more careful. And Chen-Wen will tell you a little bit about this. And then you get these elliptic integrals out of the differential equations too. And then you can solve not only the full resummation of the polylogarithm, this log of x, and so on and so forth, but also the special function part, also out of the differential equation. And we start seeing that the GR problem, the full relativistic problem in the post-Minkowskian expansion, it starts getting this special function. So the special function of resumming all these PN corrections, it starts becoming much more interesting. So you start thinking about maybe even bootstrapping, fully bootstrapping, not only in this way, which means get the boundary conditions at very small velocity for post-Newtonian and resum through differential equations the full PM answer. What if we resum in G2? And this is something that people have been starting to look at. Here is also the first time in which not only potentials matter, also the radiation reaction. We start getting this beta logarithm, so the combined angle knows about the potentials and about the radiation reaction, also about the tail effects. And this has been rederived since when we did in 2021 by other groups as well. But then you start asking, what is this calculation? Well, we're doing an angle, so we're kind of doing the conservative part of the calculation. We were thinking about radiation reaction, but the binding part of the radiation reaction. What about the dissipation? What about the waveforms? What about what we want? Well, this was eventually done, and this becomes a little bit more subtle. It becomes a little more subtle because now I cannot do, I can get the fluxes from the imaginary part of the partition function, but if I want to really follow the field, I need to use retarded boundary conditions. How are retarded boundary conditions used in quantum field theory? Well, they're used through the so-called in-in approach. The in-in approach, what it does is essentially double the number of fields. Instead of going in-out vacuum, you go in-out, but then you come back. You double the number of fields, and then you go in vacuum. And that now basically in different bases, if you stick with the original bases, you do get Feynman and Dyson propagators. But then you go to the so-called Keldysh basis, and then you get these retarded and advanced combinations, because Feynman can be written as retarded plus a cat piece, and those cat pieces are the ones that are accounting for the radiation. And we were the first to do this. We were the first to complete the full three-loop scattering dynamics for the impulse, for the energy, and so on, by doing now the full calculation for the retarded boundary conditions. But the theory remains the same. The only difference now is that the boundary conditions are retarded integrals. But the retarded integrals turn out to be way easier to calculate than the Feynman integrals. In fact, they're way more natural than the Feynman integrals. So this calculation, in some sense, was more difficult because the number of terms was large the first time we did it, at least, because the way you deal with symmetries of propagators, because the retarded flips into advanced, so you have to be careful when you do P minus P, and Feynman is symmetric, and therefore you can reduce families, you can use the integration by part tools with symmetries and so on. So that's the only part that was tricky. The actual integrals were actually simpler. So that's why retarded becomes now the natural way to do it and the natural way to track the full solution. I don't have time to talk about this. Chen Wen will tell you a little bit more. All I want to say as a message here is that what is the bottleneck of this problem? The bottleneck of this are the integrals. And not only the integrals, doing the IBP reduction is the bottleneck. And that was, for example, recently done at 5th post-Minkowski. I have 4 loops, but only at one SF order, only the first mass ratio correction by the group of Jan Plewka and collaborators in Humboldt. And everything boiled down to doing the IBPs of this calculation, because the integrals themselves were very easy, were almost the same. In fact, there were no elliptics anymore at 1SF. It was mostly just polylogarithms. So clearly, the bottleneck is having new tools to deal with this massive set of integrals that have to be reduced. Even the integrals that have higher powers of numerators that have to be reduced to lower powers. And so all this IBP technology, which Chen Wei will cover a little bit more about, is the real bottleneck of this approach. And that just computationally, then comes the conceptual part that if I have time, I'll tell you, which is how we do to map this to a bound, because so far I've been just talking about scattering. I haven't told you anything about these maps into bound. But let me just flash the results very quickly. This was the very first calculation of the full 4 post-Minkowskian 3-loop scattering impulse. The impulse can be written into a B direction. And this check is just said that I choose an orthogonal basis of the velocity. So the U check 1, U check 2 are orthogonal. And these are the answers. It has the elliptic functions that I told you. It has the dialogues, the logs. These are just another way to write the dialogues and logs. So there are different bases that you can use to write the things. These H's are just polynomials in gamma. So then this part will give us the dissipation of energy. This part, if you move now to the center of mass, which is actually moving, it might give us an angle, but that angle is not well defined. You have to be careful because now the system is radiating. So there's a little bit of subtlety now computing this conservative part of this full answer, which I don't have time to talk about, but this was in beautiful, perfect agreement with the post-Newtonian calculations of Bini, Damoun, and Geralico. This is the total energy, for example. And here I cannot resist mentioning that this corrected the calculation that was done by Kovacs and Thorne many years ago in the 70s, where they did the waveform, they computed the power, and also the post-Minkowskian approximation, but we couldn't do the integrals, the decent numerical evaluation at 3 p.m. This is the 4 p.m., so we corrected also what they did. But it was kind of funny that they had a Feynman diagram approach in their paper, even though they didn't quite use the Feynman approach or what we do. And they were also saying, oh, the quantum and classical regime don't overlap. So they were also very confused about what it was classical, what it was quantum, and so on. But I found rather amusing that they also thought about using Feynman approach, which is pretty much what we're doing right now. So then the conservative part, if you put all of this together, there is a piece there that you can sort of disentangle. It's very tricky to define what those guys are, but we made a conjecture about what the conservative and dissipative parts are, and these are the splits, and in some sense disagree with almost everything that is known up to 4pn, but then the 5pn correction has a mismatch. And this is related to these memory terms that I mentioned earlier. I'm not going to discuss this here. We are trying to resolve this problem, which might have to do with what we mean by conservative, dissipative, and how we define these things. But there's a lot of very interesting conceptual issues here in understanding from the full answer what is what. But the nice thing is that if you just look at the full answer, and then you just take the full angle, which includes everything, conservative and dissipative, and you match to numerics, and this was done by Thibault and collaborators, it so happened that it's beautiful and on the money. You have to do some kind of resummation, right? Because this is a 4pm angle. This is now a non-perturbative solution. But this resummation that I don't have time to talk about, and maybe tell you a little bit in a second, it has to do with how we will map into the bound case in something called, or what I call this First-of resummation, which is, well, now that I have an angle, I can reconstruct a Hamiltonian or a momentum or whatever you want as a 1/r expansion, and use that as the full theory, as a 1/r to the 4 G4 full theory Hamiltonian, and that reconstruct the full angle now. That's all G. For example, 1/r Newton, when you compute the angle, you don't just get G, you get G, G squared, G cubed, you get everything. Because the 1/r is an exact theory. Well, we can do the same with PM. If you do that, the answer is right on the money, which is beautiful. Somehow, this resummation of the PM results is really capturing a lot of the full numerical data. But we still don't know, as I said, how we map into bound, and that's the second part, which I probably have just 10 minutes. So I'm going to be very schematical, but I'll be happy to discuss whenever the chance arises. So let me just very briefly, how do we do this? How do we go from the angle to a bound observable? I would like to tell a little bit more, because how did I get inspired by this? How do we get, Gregor Kelly and I were looking at this, and we were thinking, well, how do we go now to an observable for, say, like the periastrum advance from the angle? And the way it was done originally is like, oh, they constructed a Hamiltonian. From this Hamiltonian, for example, the 3pm log x Hamiltonian, it becomes rather complicated. The angle is simple, but the Hamiltonian now, which produces that angle, is a mess. And this now produces that angle, obviously, and produces also a bound state observable, because now that is a Hamiltonian, I can use it for whatever I want, provided that the Hamiltonian is universal, which is non-trivial, and I'll get to that in a minute. But do you really need to do that? The whole idea of amplitudes was that you get an observable. Forget about what happens in the middle. And if you go all the string theory, then IDS-CFT, everything happens in the boundary. There is not even a bulk. So why do I need this Hamiltonian? Why I can just go from the boundary observable, like the scattering angle, to the bulk observable, like a periastrum advance, without ever talking about any gauge-dependent object? And in fact, okay, let me skip this. When this result appeared, it was even in the blackboard of Sheldon in Big Bang Theory. It was a big thing that this result was, and indeed that was amazing that they were able to do this. Don't get me wrong, but I was very surprised that they invest some time in understanding how to map the observables instead of constructing this Hamiltonian. and as I want to emphasize, we don't need this Hamiltonian. We can go directly to observable. It's not the right approach to do the Hamiltonian. As I was saying at the beginning, many of you guys heard, I'm Uruguayan, and people don't even know what Uruguay is. Actually, it's not Uruguay, that's Paraguay. Anyway, and this is Sheldon, where he had the wrong beta function in the board, and then this woman that was doing loop quantum gravity came and corrected it, and she said, well, you don't come to my house to change my board. I cannot judge doing the Hamiltonian, because that's what you want to do. That's what the PM people did, and it's completely fine. What I'm trying to say is that it's not the right mindset. You should be able to just do everything with observables. And that was our eureka moment, which is not it was the non-eureka moment. It's not that you see something and then you think about, oh, this is a completely new way of thinking right away. But you notice that something that is peculiar, something that, oh, look at this is somewhat funny. And that's, I wanted to say, this is the Asimov moment of not eureka, But that's funny because Asimov had this saying that the most exciting phrase in science is not eureka, but oh, that's funny. And that's what we noticed with Gregor, that there was something funny going on. If you look at an observable in scattering, say a scattering angle, how do you construct it? Well, you take, for example, the action, the radial action, which is the integral of the radial momentum, which is the thing, and you take a derivative with respect to the angular momentum or the impact parameter, and that gives you the angle. The periastrum advance is exactly the same thing. The only difference, in one case is negative binding energy, in the other case is positive binding energy. In this case, it's an ellipse, so the endpoints of the dynamics are, they are minus and they are plus, the zeros of the radial momentum. In the other case, you go to infinity to some minimal point, and then you just double. It's twice the same integral. That's why it's not 2 pi, it's pi, and that's what this is our mean, and here is between the points. But it's the exact same thing. So if I had a way to connect the points, I could connect those two. And lo and behold, we found that the points of the unbound and bound case, the endpoints, the zeros of the radial momentum, are connected by analytic continuation. What does that mean? That means that I can really connect those two immediately. You give me an angle, I give you the periastrum advance. And that was that funny moment, because noticing that those two things are related, now we can connect the whole observable. And not only that, from there, we get the full radial action as an analytic continuation. And not only for the periastrum advance, now we get all the observables out of the radial action. The radial action of unbound and bound are connected through analytic continuation, and you get not only the periastrum advance, you get the time delay, you get all the observables of the bound and unbound motion directly from the scheduling data. All conservative observables, because the periastrum advance is conservative and the angle is conservative. So for the dissipative part, you have to separate those two. You first take the conservative part, and then you construct the fluxes, and with that, you try to construct the waveforms. And this is also subtle, and how to extend this to the fully dissipative case is not clear, because I don't know what the periastron is once you include dissipation, but this is something that is ongoing. You can also do the spinning case. It's something that we did as well with Chen Wen and Cixi Yang. This is a beautiful equation. This equation includes the spin corrections from the angles, includes all the contributions. Yeah,
Rafael, you have 6 minutes left.
Yes,
yeah,
thank you.
6 minutes.
Yes, 6 minutes. That's very precise, as we are in precise physics. So you can do all the spinning case as well. And let me just show you how this works, because it's really pretty. You just look at the exact G-squared contribution that I told you we could calculate, the 2 p.m. correction. That gives you the exact 2 p.m. action, exact. And now you expand in Pn, all these gammas are energies, and the energies you can expand in post-Newtonian. And then you get the 1/j derivative square will give you the periastron. All the J-square periastrons are uniquely predicted by this theory. 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m., 6 p.m., all of them. All the periastron 1/j square are predicted by this formula. There is nothing prettier than this. The J4 as well, modulo something I'm going to tell you about, these tail terms, which are a little tricky. But now we have a way to directly map observables. And this is extremely useful. How do we map dissipative part? Well, that's non-trivial, because as I was saying, how do I define observables? Well, what we could do is an adiabatic approximation. We treat all the motion conservative, and we average over periods and treat all the dissipation as like fluxes. So how do we get those fluxes? Well, you can do exactly the same as I told you with the periastron. An integral of a flux gives you the total energy. An integral of a flux gives you the total energy, but now the points are related. Remember, adiabatic means conservative for the motion. Conservative points I know how to connect. So the total radiated elliptic energy is related to the total hyperbolic energy. Exact analytic continuation, but now there's a flip of sign, because here the flux obeys a plus relation. The flux of J minus J are symmetric, and like what happened before, but the angular momentum is odd. And then you go back to what happened to the periastron. So you can also relate the total flux of angular momentum, total flux of energy, to the hyperbolic, from the hyperbolic to the elliptic case. And that, again, without ever touching a Hamiltonian. Look at this. You do an analytic continuation of the hyperbolic case, which is complicated, way more complicated in some sense than the bound case, because you got these cosine terms and so on. You do the analytic continuation, which j goes to minus j, takes eccentricity to minus eccentricity. So all these cosines pick factors of pi, And lo and behold, the full hyperbolic case gives me for free the full elliptic case. And from the elliptic case, I can get a flux, and from the flux, I can get a waveform. So this finishes the story. Conservative part, I get the radial action. The separative part, I do this, and I get the fluxes, and I construct adiabatic waveform. If it wasn't for the problem I'm going to tell you in a minute, this would be the end of the story. The problem is that there is an obstruction in this, in going in this analytic continuation, because I was cheating. I was telling you that I integrated in an object like this radial action, this momentum, assuming that it was the same function, regardless of bound or outbound, meaning there was a 1/r expansion. This is true, but the coefficients are not the same between bound and unbound when you have these tail effects. These tail effects become non-local in time. They entail an integral of a logarithm of a frequency. I don't have time to explain where this comes from. It's universal, but it's completely non-local in time. This integral, when you Fourier transform, becomes t minus t dt prime. And therefore, when you expand in Pn, you get 1/r coefficients which are different. And that boils down to the energy that you get from hyperbolic or elliptic is completely different. The logarithms are universal, which is beautiful. The beta log is exactly the same. But the local part of the non-local action, local in the sense the coefficients of the terms which are integral of d, e, d omega, log omega, which is not log of v, but the other parts, the 41/20 or over 30 that you get in the unbound case, in the bound case, sorry, in the unbound case is different. And the energies are not the same. So this was a big stoppage for this whole program. Stop, don't go any higher order, because the full hyperbolic Hamiltonian that we get, ourselves, B, everybody, it fails to describe a bound system. So what are we going to do? Well, it's sitting in front of us. This guy is
Rafael,
universal. Why? 1 minute.
Rafael, you might need to wrap up because we need time for questions also. 1 or 2 minutes.
Okay, so then let me wrap up. We did this. We
Yeah.
subtracted this term. I finished. We subtracted this term. We construct the full now local Hamiltonian, which is completely universal, and the logs, which are now also universal, as I told you. And this matches beautifully the full bound dynamics. So now we have a way not only to get the full thing hyperbolic, but also getting the local part of the dynamics, and Chen-Wen hopefully will tell a little bit more about this. So where are we? We control the vertical and the horizontal. We get PN and PM data. We are moving forward. There's a lot of conceptual and computational things that we need to get through. It's not the end of the story of just cranking and pressing enter. There's a lot of things to do. We want to get to high orders. We are not ready for the future. Thank you very much for your time.
Thanks, Rafael, once again for the great talk. So the floor is open for a quick question. Please raise your hand if you have a question.
There was something in the chat. I'm not sure if that was a question.
No, I
Hey,
don't
Rafael,
think,
this is Alok. Can I ask a question?
Yeah.
Alok?
Yeah,
Oh,
Alok,
hey.
sure, go ahead.
Hi. Hey, hi. So this
I cannot see you. Where are you?
Yeah, my camera is off.
Oh, I see. Okay.
Yeah.
Go
No,
ahead.
I wanted to ask about this Damour and Bini result. They had this curious mass polynomiality. When they were computing the scattering angle, they had this mass polynomiality constraint on when they included all the radiation reaction terms. I was just wondering, did you also have this in your way of doing things?
Yeah, we predicted this. What Thibault noticed
I see.
was
Yes.
general. Thibault noticed what we did at 2 p.m. with Gregor. We actually,
Yes.
Gregor and I, we pointed out precisely this, that there's a mass polynomiality, because if you look at the answer from the point of view of scattering, it's almost trivial. The diagrams comes with insertion of the sources, which are masses. So obviously, the mass dependence of the impulse is just determined by the sources. And now all the dynamics in the angle that comes from that impulse is uniquely determined by an impulse which is symmetric in M1 goes to M2, because in the conservative part at least, because the delta P1 plus delta P2 is 0. And therefore, you have to come in the combination M1 plus M2. All this mass polynomiality from the point of view of the impulse is semi-trivial. What Thibault noticed, though, and we mentioned with Gregor only at 2 p.m., Thibault and Donato and company, they
Yeah.
notice that this extends to higher orders, is that because when you go and compute the angle from this delta P, you do this funny thing. You divide by this P infinity.
Yes.
Delta P divided by infinity gives the angle. This P infinity now knows about the energy. It knows about this gamma. I don't know where I had it. Here, this gamma. Because the P infinity knows about it. This gamma now has all these nus, these masses.
Right, exactly.
But it enters just with this 1 over gamma. And therefore, all the mass dependence is all inside this 1 over gamma. And therefore, the full result, the whole mass dependence, I can uniquely get from these 1 over gammas and the masses in the impulse. But what we show recently is that this whole polynomiality is great, but we have a problem. It applies only to the total answer. If you now go to the local part, which is the one that is universal, because the no local part I cannot use for bound, the whole answer, where is it? Here, this whole answer here, when we subtract the local and non-local part, it breaks this polynomiality. So this polynomiality in the universal part is gone. Why? Because this non-local term up here, this omega, is the center of mass frequency of emission, depends on the mass now. It's like the energy times dotted with the U of the center of mass.
Yes.
And that puts masses into the problem. And as Chen Wen will explain, this completely changes the solution. And therefore, this mass is beautiful for the full answer, but not for the local and non-local separate, which are the ones that we think we can map between bound and unbound. So,
thanks. I see.
For hyperbolic, the mass is uniquely fixed. For non-bound, for bound, it's not.
Okay, thank you. Thanks.
Okay, so I think we need to stop over here because we are out of time. Once again, thanks, Rafael. And further questions can be communicated to the speaker directly. So now